In probability, we have a term called expected value. And basically what we're trying to say is if a situation were repeated over and over and over again, what would you expect to happen in the long run? So sometimes this term expected value is referred to as the long run average. Sometimes it's referred to as just the mean. You can think about that like the average. And let's do an example, and then I'll kind of explain what those terms kind of apply to. So let's say you play a game where you roll 2 die. If you roll doubles, you win $5. Anything else, you win nothing. So let me just start off by listing our outcomes. I'm going to call those X. I'm going to use some variables here rather than just writing words all the time. So we have 2 outcomes when we play our game. We can either win $5 or we can win nothing. Now below that, let's write the probability of each of those outcomes. Now from previous work, from previous videos, I hope you remember that there are 36 total outcomes when you roll 2 die. 6 of those outcomes are doubles because you could get 2 1s, 2 2s, 2 3s, 2 4s, 2 5s, and 2 6s. So the probability of rolling doubles is 6 out of 36. Of course, that reduces to 1/6. So the probability of not rolling doubles, and therefore winning nothing, is the other 30 out of 36 outcomes. Now, if I were to simply ask you, without any probability, that these are the 2 outcomes, and you say, okay, well, what's the average outcome? Well, in math, we always add up the outcomes and divide by the number. So you could think to yourself, well, 250 is right in the middle of the 2 outcomes. But the top outcome is much less likely than the bottom outcome. So we need to tip our scale here. We can't say it's 250. It's got to be tipped towards 0. And that's where probability comes in. So our formula for expected value is we take our outcome and we multiply it by its probability. The higher the probability, the more that outcome counts. The lower the probability, the less that outcome kind of matters. So starting with that, I'm going to write those calculations. We've got the probability times the outcome. And then we've got the probability times the outcome. And much like we always do with an average, we're just going to add those together. Now, if you think to yourself, well, why aren't I dividing by the number of outcomes like I do normally with an average? That's really what the probabilities out front are doing. We're already dividing by basically the number of outcomes that were possible. And we're weighting them like 6 ways to get $5, 30 ways to get $0 out of the 36 possible ways. So that's why we don't have to divide. Now, this calculation comes out to be, and I'm going to round here, basically 83 cents. Okay? Now, a couple of things. First off, you'll notice that 83 cents is not a possible outcome. That shouldn't throw you off. Oftentimes, the average or the mean is not a possible outcome. When your class takes a test and the teacher says the average is 82.2, no one got 82.2, but we all understand that's the average. Now, another way to think about this is that every time you play, this is what you expect to win, 83 cents on each play. Another way to think about it, this kind of long-run average way, is to say, if I played the game over and over again and I kept a tally of how much money I'd won and how many times I'd played, at the end of the day, I should be able to take the total amount of money I won, divide it by the total amount of times I played, and it's going to be very close to 83 cents. Okay, so that's that long-run average. Let's do one more example. From previous visits to Target, you estimate the probability that one employee-run checkout lane will be open is 0.1. 2 lanes, 0.2, 3 lanes, 0.6, and 4 lanes, 0.1. Find the expected number of open lanes. So let's make a quick table of our possible outcomes. And notice I said employee-run, so we're assuming, of course, the self-checkouts are open, but we're not counting those. So we've got 1 lane open, 2, 3, and 4. Below that, let's write the probability of each of those outcomes. We've got 0.1, 0.2, 0.6, and 0.1. So again, if I just said what's the average, it'd be tempting to say, well, just add these up and divide by 4. But again, these ones are more likely than the edges. We need to somehow show that, and of course 3 is the most likely. So again, using our formula, which is take the outcome and multiply it by the probability, we'll have 0.1 times 1, 0.2 times 2, 0.6 times 3, and 0.1 times 4. And then we do the summation of that. We add those up. That's what that symbol means. If you haven't seen that before, this is sigma. That stands for add those together. And if we do that and calculate it, we get 2.7. Again, it's not possible for 2.7 registers to be open, but this is the average. So if someone forced you, they said, well, I'm going to Target, how many lanes would I expect to be open? You'd say, well, between 2 and 3, probably more likely to be 3 than 2. Again, another way to think about it, if you went to Target many times, always noted the number of lanes that were open, and then at the end divided by how many times you'd gone, you'd probably get close to 2.7. So this is expected value. This formula is worth remembering. Remember, it's just a way to find the average where we basically change the weighting of our outcomes. If this video helped you, please like and subscribe for more math help.